Hey guys, how's it going? As you may have noticed, I have a few new hand tattoos going on here, and I just wanted to show them off real quick, get your opinion on them. No, actually, the reason I've got these hand tattoos is because they are related to today's lesson, which is on the right-hand rule, and this equation right here that you may have seen referenced in the previous video. All right, now, this equation for oh, look at those fingernails. For force is the force exerted on a moving charge in a magnetic field. All right, now, I'm sorry if you're laughing about the strangeness of my hands. I kind of am too. My nails, they look so pretty. It's just dry erase. It'll come right off. Don't worry. In the equation QV cross B, we've said what all the individual pieces are, right? Charge, velocity, magnetic field strength. But what we haven't talked about is this little x right here. It is not just a multiplication x. It's a cross product. I seem to remember cross products somewhere else in physics. That's right. You may remember them from somewhere else. The somewhere else is actually torque. When we talked about torque, right, we had F cross R. And the deal with torque, brief reminder, the deal with torque was, in order for there to be a torque, force and radius had to be at least a little bit perpendicular, right? If you had something like a wrench that you were trying to use to turn something, now I have to remember how to draw a wrench. This wrench will not work. Okay, whatever. We'll just go with it. All right, so if there's the wrench, right? If I push this way, it's not going to turn it, right? That will not help me in any way with this problem. However, if I exert a force like this, that will give me some torque. So F being applied perpendicular to the handle, which would be the R, the radial vector, that would give you the amount of torque that was being applied. Okay, so the rule there was perpendicular, and that was pretty much all that we worried about there. So as far as that goes, we can talk about that little bit. This equation is often going to be written as QVB sine theta for that reason that I just discussed. There will be no force unless the velocity and the magnetic field are at least a little bit perpendicular. Okay, so what that looks like is this. If you had a magnetic field that was going in, say, this direction, and you had something move into it, say a proton, going like that, it would experience no force. Okay, so in order for there to be a force on that charge at all, the magnetic field and the velocity have to be at least a little bit perpendicular. All right, now if we had a magnetic field like this, and the charge is moving into it, then there's going to be a force. But now, what will the direction of the force be? Well, that's a pretty important question, and it's actually the one that I need all these hand tattoos for, is to try and discuss which direction that force even occurs in. The bizarre thing about magnetic fields is this. Most things, most forces, the force is parallel to the field. Not so the magnetic field. Well, Mr. Errico, is it going to be parallel to the velocity then? No, it's not parallel to the velocity either. It is in fact perpendicular to both B and V. And if it's got to be perpendicular to both of these, we're now dealing with a really awkward situation in terms of drawing it. That is that the force here, the only directions that are perpendicular to both of those would be this way, right, coming right at you, or this way, going directly away from you. Ooh, boy, that's tough to draw. Well, you know what? It is tough to draw, so we're not going to do it. No, I'm just kidding. Of course we're going to do it. That'd be silly for us to shy away from difficult things. So the way that they resolve this is with notation, and also by most of the time making the magnetic field be the thing that goes into or out of the page, but not always. All right, now, if you see these, like a whole bunch of these arranged around, or sometimes they'll just draw dots. I'm going to stop drawing because it gets tedious. Dot, 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 dot. Okay, if you see this, either of these things indicate a magnetic field, which is out of the page. All right, so either of those would indicate that. Now, what about X's? That's the other notation that you'll see. These indicate a magnetic field that is going into the page. The reason they picked these is actually they were thinking about magnetic field vectors as being like a literal arrow. So if you have a literal arrow, the X, so it's like you're looking at it either head on or tail going away from you. So if you think about this arrow flying away from you, right, what you could see would be the fletchings. That's what the X's are supposed to be. If it was coming towards you, then what you would see would be the point. Okay, so these are the point of the vector arrow, and these are the fletchings of the vector arrow. That is the crazy reason for that notation right there. Okay, now, what then do we do with all this? So if we had, let's say, a proton moving into one of these fields right here, there's this thing called the right-hand rule that you use to predict the direction of the force. So notice, here's my right hand. My left hand is undecorated because in this circumstance, it is useless. I need my right hand for this. If you try to do it with the left hand, it doesn't work. If you are thinking, well, my two hands are the same, no, they are not. They are mirror images. And that means that they give opposite answers if you try to do the right hand rule with your left hand. So unless you don't have a right hand, you should use your right hand for these. All right. So the way this works is as follows. My thumb is the direction of the force. It was supposed to be purple. I don't know if you can see my thumbnail being slightly purple, but the purple marker was just not up to it, so I ended up going back to black. All right. The magnetic field is my index fingers, and my hand, the sort of plane of my hand, is the velocity of the charge. So if I have a charge moving this way, right now the force on it will be 0 for the reasons that we discussed, right? Now you always are going to hold your thumb to the best of your ability perpendicular to your hand. Okay, so if V and B are parallel, for reasons we discussed already, the force is actually going to be 0. All right, now in the event that they are perpendicular, that looks like this. And the length of my thumb corresponds to the magnitude of the force. Or in this case, really, it's mostly just the direction. Let's try that again. So if we have a charge that's moving, say, this way into a magnetic field that goes that way, the direction of the force would be directly towards you in the direction that my thumb is pointing. So we're going to do a bunch of examples. So let's take this one here. If I've got a proton moving to the right into a magnetic field that is pointing, oh crap, that's out of the board because that's the point of the arrows, and I want to find the direction of the force on it, well then I am going to point my hand like that. All right, see my red arrow pointing in the direction of the velocity. All right, my fingers now I need to curl in the direction of the magnetic field. Well, my fingers don't, how do I get my fingers to point up towards the screw? Oh, I have to rotate my hand. So there's going to be a lot of rotating your hand going on. All right, now you can't really see my various arrows that I've drawn because my hand is flipped over, but it seems that my thumb is pointing down the screen. So that would be the direction of the force. So let's review that again, right? If V is that way, right, and the magnetic field is out of the page, then this is how I must orient my hand in order to be in keeping with those. And then my thumb, which should always be pointing perpendicularly away from my hand, is pointing down the page. Therefore, that's the direction of the force on that proton. Okay, so we'll draw that in. F. There's the direction of the force. Well, what about if the field had been in some other direction? Well, let's do a different problem. What the heck? Let's do two problems in one. All right, so I've got a velocity that's up the page. There, see, up the page. All right, the magnetic field is, X's are away, so that would be into the page. So I have to, again, rotate my hand because my fingers don't. All right, so I have to turn my hand so that my fingers can point in the direction of the magnetic field, and my thumb points that away. So this one experiences a force to the the direction that the left. That's what that is. Okay. The other one, let's see. So if V is that way and B is into the page, I have to orient my hand like this. All right. V is that way. B is into the page. And I now have a force which is to the right. So because their velocities were in opposite directions, those two protons experienced forces in opposite directions. All right, now, I keep talking about protons. If it's an electron, something interesting happens, and that is the directions all switch around. So if it's let's say a negative charge of some kind, flying in here like that, and I do the right-hand rule, the result that I get is for always a positively charged particle. Okay, so if I'm pointing this way for the velocity, magnetic field is into the page, I will get that the force is up the page. Well, since it's an electron, that means the force will actually be in the exact opposite direction. Okay, so a negative charge receives the opposite answer. Mr. Errico, I have an idea. I will use my left hand for negative charge. Don't do it. Don't do it. The reason I say don't use your left hand for negative charges is I want you to only be in the habit of using your right hand. Your right hand. That's it. Don't use any other hand for analyzing forces. Instead, take the mental step of saying, oh, and it's negative, so I reverse the direction. Have it be a mental step rather than a physical step where you decide which hand to use, okay? Because most of the time, probably you won't think about which hand to use because it should be automatic, okay? So use your right hand, but just remember to switch the direction of the force for negative charges. All right, I think we'll have to break for another video in which we will look at all of these ones in example 1.